Today, we are diving headfirst into one of the weirdest, most mind-bending ideas in all of physics. The idea that solid things, the very particles that build our entire world, can act like waves. Yeah, you heard that right. Let's get into it. So, to even begin to get our heads around this, you have to start with this absolutely central paradox in quantum mechanics. It's a question that experiments have literally forced us to ask. How on earth can a single particle, just one little photon or electron, be in two different places at the exact same time? It sounds completely impossible, right? But the universe is telling us something else is going on.
All right, so let's look at the evidence. The whole mystery really kicks off with this idea of a single particle that somehow, someway, seems to take two different routes at the very same instant.
Picture this. In a lab, scientists can shoot out just one photon at a time, a single particle of light. They send it towards a fork in the road, two separate paths it could take. But here's the crazy part. When those paths come back together, the photons build up an interference pattern. Now that kind of pattern can only happen if waves overlap, which means each and every one of those single photons had to have gone down both paths at once to interfere with itself.
So how in the world do we make sense of that? Well, this is where physicists had a breakthrough. They figured the particle itself isn't literally splitting in two. Nope. Instead, what's traveling is something called a probability wave. Think of it like this. The wave isn't the particle, it's a wave of all the possibilities of where the particle could be. It spreads out, it explores every single path available, and the way those possibilities interact determines the most likely spot we'll find the actual particle when we finally decide to look.
Now this idea didn't just pop out of thin air. It really started with a super daring proposal way back in 1924 from a French physicist named De Broglie.
De Broglie's thinking was just beautiful in its simplicity. It was all about symmetry. He just looked at the science and said, okay, we know light is a wave, but it acts like a particle, a photon. So why can't it work the other way? Why can't a particle, like an electron, act like a wave? It was such a simple, elegant, and totally revolutionary question.
And this question gave birth to the whole concept of the matter wave. De Broglie basically proposed that any particle that's moving has a wavelength. And the key thing is, that wavelength is directly tied to its momentum. The more momentum it has, the faster or heavier it is, the shorter its wavelength gets. And that's crucial, because it means for big stuff, the wave-like behavior becomes almost impossibly small to see. A daring idea is one thing, but in science, you've got to have proof. And let me tell you, the visual proof for matter waves it's just absolutely stunning. So think about that famous double-slit experiment. But instead of light, we're going to fire electrons, tiny, solid bits of matter, one at time. What do you think you're going to see on the screen on the other side? At first, it looks exactly like you'd expect. The first few electrons just hit the screen in what looks like totally random places. Just a few scattered dots. Nothing weird here, right? But you keep it running. You keep firing those electrons, one after another. And as the number climbs into the thousands, something incredible, something impossible starts to happen. You can start to see it. It's not random anymore. Little stripes, these bands of where electrons are landing and where they're not, they're starting to form. Each electron, all by itself, is somehow helping build this bigger collective pattern. And then, after 70,000 electrons have made the trip, boom, the result is just undeniable. It's a classic interference pattern, the exact kind that only waves can create. This picture right here is the smoking gun. Every single one of those electrons acted like a wave, went through both slits at once, and interfered with itself. Incredible. And if you're still not convinced, just look at this side by side. On the left, that's a pattern made by X-rays, which we know are light waves hitting a crystal. On the right, that's the pattern made by a beam of electrons hitting the exact same crystal. They're identical. They're practically twins. The conclusion is just inescapable. Electrons behave like waves. So this just throws open a brand new door, right? If electrons can be waves, what about bigger things? Where does all this quantum weirdness actually stop? Well, scientists have pushed it. They've confirmed wave behavior in protons and neutrons, which are way heavier than electrons. They've done it with whole atoms. They've even done it with giant iodine molecules, which are 500,000 times more massive than an electron. And get this, they've even seen it in these complex molecules called buckyballs, which are shaped like tiny little soccer balls. So does this mean your cat is also a wave? Can it be on the couch and in the kitchen at the same time?
Well, thankfully no. As the textbook so perfectly puts it, there's a limit. For big, everyday objects, the wavelength becomes so unbelievably infinitesimally tiny that you could never ever detect its wave properties. We are safely in our normal classical world, and I'm sure all the cats are pretty relieved about that.
But this leaves us with one last really nagging paradox. If electrons are really these spread-out waves, why do we always see them leave trails that look like they were made by particles?
I mean, you look at a photo from a bubble chamber like this one, those elegant, curving lines, those are the paths of individual electrons. And they look like solid, definite tracks, not like a big, fuzzy, spread-out wave. So what's going on? How can both of these things be true?
Let's just put the question out there directly. If an electron is fundamentally a wave of probability, spreading out and exploring all kinds of paths, why does it end up leaving a single, neat, straight line of bubbles?
And the answer, believe it or not, comes right back to interference. So that matter wave goes out and explores every possible path between 2 points. But here's the trick. For every weird, curved path, there's another path right next to it that's almost identical, but just a little out of sync. And what happens when waves are out of sync? They cancel each other out. That's destructive interference. The only path where the waves are all perfectly in sync is the straight one. They all add up and reinforce each other. That's constructive interference. And that is the track that we see.
So in a really poetic way, that track we see isn't the path of a tiny little billiard ball at all. It's more like the ghosts of the wave's journey. It's the one single path that survived this whole quantum process of elimination. The wave and the particle aren't fighting each other. One actually creates the other.
And that leaves us with a pretty deep final thought to chew on. You know, we think of reality as being solid, made of definite stuff in definite places. But the evidence is pretty clear. At the most fundamental level, everything is governed by these weird waves of pure possibility. So it makes you wonder, if the world is truly built on probability, what is reality really?